This is a quick video on net ionic equations of acid and base reactions. First thing you need to understand, I guess, is what an acid is, what a base is, which we've talked a little bit about. So remember, acids are giving away hydrogens. Bases are hydrogen acceptors. So I think about that. Every time you think about it, an acid is always getting rid of a hydrogen. So water can actually act as an acid. It can get rid of a hydrogen. It can also act as a base and accept a hydrogen. So most things are either acids or bases, or some things are neutral. But again, giving away a hydrogen is an acid, accepting one is a base. So acid-base reactions, obviously one thing is giving a hydrogen, the other thing is accepting the hydrogen. Remember your strong acids. Okay, we've gone over quite a few times. So you got your hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric, chloric, or perchloric. Okay, so you got your 6 or 7 strong acids there you need to know. Remember, strong bases would be hydroxides from family 1. So lithium hydroxide, sodium hydroxide, potassium hydroxide. And then calcium, strontium, and barium hydroxide would be considered strong as well. So we're gonna break up the 3 types of acid-base reactions into a strong acid with a strong base. It's the simplest reaction. A weak acid with a strong base, and then a strong acid with a weak base. So remember, the difference between a strong acid and a weak acid is that a strong acid completely splits apart, produces a bunch of hydrogen ions, and a weak acid, only a small percentage of the molecules split apart. The majority of them stay together. Same thing with bases in terms of producing hydroxide ions. So strong acid, strong base would be like this. This is the easiest one, like I said. So if we have a strong acid such as, actually I'm going to change that. Let's do hydrochloric. This probably make a little more sense to you. Strong acid such as hydrochloric. So remember, that is aqueous. It is strong, so that means it completely splits apart or ionizes into its ions. So you'd have aqueous hydrogen ions, aqueous chlorine ions. Sorry about the glare on the screen here. Let's say that's reacting with a strong base, such as sodium hydroxide. Again, a hydroxide from family 1 is considered strong. Again, if it's strong, that means that all the molecules will split apart into ions. So you'd have sodium ions and hydroxide ions. So remember, those are aqueous. Those are in solution. So you have 4 ions floating around in solution. Hydrogens, chlorines, sodiums, hydroxides. Okay. Now, last year you would have written this reaction as a double replacement. You would have written NaCl, which is table salt, plus water, or HOH, hydrogen hydroxide. Well, sodium chloride is soluble, so it would be split into ions. Water is a liquid, so solids, liquids, and gases are together as molecules, so we'd have plus H2O. Well, let's look at our net equation. We have a lot of spectator ions here. Sodium is a spectator ion. So they're at the beginning of the reaction, they're at the end. Chlorine, spectator ion, they're at the beginning of the reaction, they're at the end. So a strong acid, strong base, the net ionic equation for a strong acid, strong base is hydrogen ions plus hydroxide ions form water. Okay. As long as they're in equal molar amounts, you get only water. Now, if we had more of these than those, then you have a limited reaction situation. You'd have some hydrogens left over. But if you think about this, strong acid produces lots of hydrogens. Strong base produces lots of OH negatives. At the end, you end up with a neutral solution. Whenever you have equal hydrogens, equal hydroxides, you have a neutral solution. So strong acid, strong base, net ionic, H plus OH negative gives you water. One thing you should always know also, a strong acid, strong base reaction always produces water and some kind of salt. In this case, it was table salt. It's not always table salt, but usually always produces a salt and water. All right, that would be considered the simplest reaction, I would say, of the 3. Weak acid, strong base. So what you need to remember is weak acids stay together as molecules. We will not split them into ions. Very few of them split apart. Strong bases will split apart into ions or ionize or dissociate into ions. So this is acetic acid, which is vinegar. Okay, so we have weak acid, so that will stay together as a molecule, so we do not split it into ions. So we write CH3COOH By the way, that is the hydrogen that is typically ionized. Okay, this is the acetate ion. That's the hydrogen. I know it's different than most acids with the hydrogen in front of it. You actually could write it that way. Sometimes written as HC2H3O2, hydrogen acetate. So that is still acetic acid. Plus sodium hydroxide. So again, that is a strong base, so we just split into ions. So if you think about it, remember, acids are hydrogen givers. It's going to give away hydrogen. Bases are hydrogen acceptors. So if you think about what's going to take the hydrogen here, hydrogen's a positive charge. You're not going to have sodium hydride. You're going to end up with HOH again. So that is given to the base. So we end up with water plus the acetate anion, negative acetate ion. Sodium is to be spectator ions. We do not need them to be part of the net ionic. They are just spectator ions right there. They'd be there at the end of the reaction also. Think about this for a minute. This is a strong base and a weak acid. Who wins, I guess, would be the battle. Well, at the end, a strong base is stronger than a weak acid. So at the end over here, we have this thing, which is actually a weak base. It has the ability to take a hydrogen. It has a negative charge, has the ability to accept a hydrogen. Okay, so it acts as a weak base. So at the end, our solution will have a pH greater than 7. Whereas in the first one, it was exactly 7 because it was strong and strong. So again, anything that's weak, we stay together as a molecule, do not split apart into ions. Okay? A few of them will, that's why some hydrogens are given there, but some of them stay together as molecules. This reaction probably would go to completion if there was enough OH negative to take those hydrogens. When we get into equilibrium later in the year, you'll understand strong acids, or excuse me, weak acids and bases a little better. All right, next one is a strong acid, weak base. A strong acid, weak base. So again, a strong acid we'd write as H+. You know, if it was HCl, HNO3, H2SO4, it still is just H+ in solution plus some kind of anion. The most common weak base, as a matter of fact, the weak base that I almost always will use will be ammonia. Okay, compounds that are called amines. They're derivatives of ammonia. So ammonia looks like this. It's got a hydrogen, got 3 hydrogens off of it. There could be a carbon chain off of this, such that R is right there. So there might be a carbon chain coming off of this, or there might be a carbon chain off of this. Okay, but they're still considered weak bases. So anytime you see that NH, it's considered a weak base. It has the ability to accept a hydrogen. Okay, it has the ability to gain hydrogen. For example, if I put NH3 in water, two-sided arrow, because not very many of the molecules actually do this, but you can't even see the two-sided arrow probably with that glare, sorry. But it is a weak base. It has the ability to take a hydrogen. It takes a hydrogen from water. Forms NH4+, plus OH negative. So if you think about that, that is not a strong acid weak base. That's just showing what NH3 does in water. That's how NH3 produces OH negative ions. It takes a hydrogen from that. That's why it's considered a weak base. Again, not every molecule does that. Okay, so let's say we have nitric acid reacting with ammonia. So we have strong acid, weak base. Strong acid, weak base. So remember, weak base we keep together as a molecule. Anything that's weak. Strong we split apart. So we'll split this into hydrogen ions and nitrate ions. Again, acids are hydrogen donors. Bases are hydrogen acceptors. So the acid gives a hydrogen to the base. So we end up with the ammonium ion plus NO3 negative. Well, remember, those are spectators, so we do not need to include those in the reaction. So our net is just that the base, the weak base, is gaining a hydrogen from the strong acid. Think about this again. The acid is stronger than the base. This thing over here is actually a weak acid. It has the ability, it has an extra hydrogen, it has the ability to give a hydrogen away to certain things. So our pH here would be less than 7. When we've reacted equal amounts of that and that, we'd have a pH of less than 7 because there's going to be a weak acid over there. There is a chart in your book here, okay, that talks about this. But if I just give you a quick rundown, I think the chart is on page 83, 84, something like that. The reacting species. So for example, strong acid, strong base, reacting species from the strong acid is H+, from the strong base is OH negative. Okay? And they would form water. Weak acid, strong base, so for a weak acid, I'm going to write, that's the weak acid. It stays together as a molecule. It has hydrogen with some part to it. Strong base, the reacting species is OH negative. Okay, and you get water. Again, acid is giving to the base plus some anion. Okay, in the first one up here, obviously, we're going to get just water. Strong acid, weak base. Okay, strong acid, weak base. So again, the reacting species for strong acid is H+. The anion is always a spectator. Weak base, we write the whole thing. Okay, for weak base, write the whole thing. I'm just going to write a B here for that. Those come together and form that weak acid. Right, so those are just general forms of that. Try the ones down at the bottom here. We'll talk about those in class some point in time.